Okay, I'm gonna use this video to talk about how to run DDSCAT and so that you can follow me. So I'm gonna mute my video because you don't need to see me. All right, so you should be able to see the screen on here, which I kind of prepare a PPT. I haven't prepared. I just wanted to show you how to run DDSCAT to determine optical properties of plasmonic nanoparticles. Now, if you knew a little bit, plasmonic nanoparticles referring like gold nanoparticle, silver nanoparticle, and these particles has attracted a lot of attention in the last 2 decades something. So you can prepare these gold nanoparticles with size like 10 nanometer or even smaller to up to 50 nanometer, 100 nanometer. I'm talking about diameters. And then they have very vivid colors. But this kind of behavior, the optical properties actually can be calculated using a software called DDSCAT. Okay, so you can read upon these later on, but what I wanted to do is directly show you on the computer, on HPC, how do we run DDSCAT. So can you see my screen here, which is on HPC? I logged in, and okay, so I'm at my home directory. Let me clean the screen, and then you can see I have a lot of stuff, right? So all my work related to this optical properties, plasmonic properties under the directory called DDSCAT. So I would recommend you to make a similar directory. And then I'm gonna making a directory called test student. I made it yesterday, so I'm just gonna go to test student. Okay, so right now I'm gonna show you to, like, if you want to calculate a gold nanoparticle 50 nanometer, what is the optical property absorption look like? That's what you do in the DDSCAT. So to understand that when you try to run a job on our computer, high performance computing, there are two type of things that you need to take care. One is, we need to figure out the software we use is called DDSCAT. So we need to specify the executable of DDSCAT, and then we need to prepare the input files that you need used for DDSCAT. But the another layer is that we are on HPC. You don't just submit job. There's a queuing system. So the queuing system we use called SBatch, and it's a very common queuing system. So you may want to let me open a web browser to show you a little bit. You can just it's called it's called a Slurm. Okay, Slurm workload manager. So here is all about Slurm, how it works, and it's learning these probably for you is a little bit overwhelming. So you don't have to learn. We always use shortcuts. We give you this the scripter to run the job, and then you slowly figure out. So anyway, so just remember 2 things. That you need to talk to the Slurm, the workload manager, and you need to prepare the DDSCAT input file and executable. So for this one, I go to 50 nanometer. Okay, I already made directory here. And so first thing you need to do is you need to prepare input file. So the input file, I put everything in the files. So it is under files over here. So wow, I have a lot of and I think I accidentally created files and another file. So I'm not going to move all the files under the file, everything in this directory. So I'm in the files, and I'm going to remove that directory files. Okay, so I'm at directory 50 nanometer files, and then these are the input file. Now, the one that you really need is the first one is called the silver dielectric tab. Okay, this is the experimental data of the silver dielectric properties, and we just handcrafted these, and you can just copy from us to keep using. But I'm running a gold, so I'm missing a gold dielectric constant. So I saw that earlier, I have it here. So I'm going to move this gold dielectric tab into files. Okay, you can find these dielectric property files in my directory. Some is called gold dielectric tab 2, some is called 1, but essentially they are the same. So we're going to actually use this one. Yeah, okay, this is the gold dielectric, and this is the data is obtained. The references show up there, right? Halik 1985, and I think I have another dielectric file, which is from another source called the dielectric tab 2. Okay, so these are the minor things I need to care. So I'm going to clean up my directory a little bit. You don't need this aspect here. You do need sphere.data. Okay, you need to prepare. So this sphere.data and how you prepare it is all talked about in the DDSCAT manual. But what we will use here is we use only one sphere. So we put number 1 here. If you're using 2 sphere, you would say 2 and 3, okay? And then these are 3 comments like 4, 1, 2, 3, 4. That means that you write anything here for your references, but the computer, DDSCAT computer, does not really read it. And then the next line is important. This is the coordinate of the sphere, x, y, z, okay? And 50.0 is the radius of the gold. So I put gold 50. So that means really gold is 100 nanometer gold when you put radius 50. And then these 6 number is related to the dielectric constant. And when you put 111000, I know it's kind of strange. It's an isotropic gold nanoparticle. The dielectric property will be specified as material 1. Material 1. Okay, and then you wonder, where do I specify material 1? So another very important file is DDSCAT.par. And this, you should copy it from my directory and then understand that these are the input parameters you need for the DDSCAT route. And so you should copy this, and then I tell you the things that you need to worry most of the time. Most of the time, you don't worry the beginning part, okay? And you don't worry here. What you need to worry here, this is the important one. This thing can be changed depending how you run it. So right now, this called the sphere PBC. That's like running using multi-sphere, but it's a periodic boundary condition. But I don't want to use that one right now. So I'm gonna actually open my Mendeley, which I have a DDSCAT manual, and yeah, you should download the DDSCAT 7.3 manual to yourself so you can look up DDSCAT manual. Okay, so and we can look up DDSCAT manual, what is sphere PBC, and these are all explained all in the manual, and you will become really very good. All right, so here, did you see, as with DDSCAT, these are the options that line counts. Oh, sorry, sphere. I'm looking for the argument I used. What is it called? SPHRN PBS, right? SPHRN PBC. Right, there you go. Okay, so notice target generation method. So there's a lot of different ways you can run DDSCAT. So SPHRN PBC is one of the way that you can run. Now you don't necessarily have to run, and there are more. Where's the option? Yeah, here's sphere. Okay, let me see. I'm gonna use this one, sphere N, the multi-sphere target unit of N sphere of single isotropic material. Okay, I'm gonna use this one instead. And so how do you specify the input file? You use this argument sphere-n. I'm going to switch here and I'm going to change this. Change it to sphere, SPHERES, N. Right. SPH, you have to be very careful, ERES_N. Okay. And then the next line, this talked about here, the next line is shape 1, shape 2 file name, right? Shape 1 is the target diameter in the x direction in the units of D. D is referring the dipole distance. Okay, so I'm going to use a 200 lattice, 200 D, 200 lattice unit. Okay, so that's the first one. Shape 2 and shape 3. So I need to delete these. Yeah, originally I used the I was using the other argument, so the input is slightly different. Spheres underscore n. So the first one shape 2, and the second one 0. Shape 2 is 0 to have A1 100 target frame, and A2 is 010 target frame. And if you want to understand what it is referring to, then you just have to read the manual to understand. Shape 2 is 1. If I set shape 2 is 1, then I'm using the principal axis moment of inertial tensor for A1, A2. Okay, I don't need anything. I think we just need shape 2 is 0. And then immediately, yeah, this is the shape 1, shape 2, and then file name. And the file name I say spheres.d. Okay, what is spheres.d? That's this guy. Remember this guy I was talking about? So this is you need to create it. And then this one you need to create it. Okay, and then you need to tell how many number of dielectric material. I say 1. So did you remember in the sphere.d, I say this number indicates what's the this number here indicates what's the dielectric constant. That's 1 corresponding in your DDSCAT when you say 1 over here. Okay. All right. So that's this. And then let me switch over. I always use Emacs. Emacs allow me to open 2 files and switching between them very good. Another thing you need to change is here. So what is the material 1? So now you need to say what particularly dielectric constant you want to use. So we want to say we want to stay with gold. We don't want to stay silver. So I change the gold dielectric.tab. And then you need to make sure, do I have this file? Yes, gold dielectric.tab is here. So this is good. Okay. And then some other parameter over here that later on you might want it to be careful is this argument. This one. It's a near field, but right now I set 0. That means I don't calculate near field. And if I calculate near field, then we need to do extension and so on. So, but you don't have to worry right now on this one. So let me what's the other thing you wanted to worry? So I'm going to explain a little bit more. Something else that you need, usually you don't worry about these things. These are default settings. We don't worry. And I want to explain one thing here. Notice this one. This is you're supposed to input the wavelengths, and DDSCAT can calculate the scattering property absorption curve from what wavelengths to what wavelengths, and it is in it is. This is a starting and ending, and but the way we set up the rounding is that we actually set up. We will set the DDSCAT round in a bunch of jobs, and each job, the lambda value is controlled through the scripting. So this input file, the lambda, will be replaced by the numerical value through a scripting file. And it's going to be stepping from, say, 400, 405, 410, 500 till 900 in increment of file. So this is something else that's me pointing to you what is changing. And this is changed later on in another scripting file. Okay, I haven't copied it here yet. So if you want to specifically run something, then you should change the wavelengths here. But follow the procedure that we have. And another thing you should be very careful is here that you do need to change this one, effective radii. And I say we want to run 50 nanometer, right? So that's 0.05, 0.05 effective radii that you used. The DDSCAT is able to run jobs like a series of different particle radius, and they just keep running different wavelengths and so on. So, but we don't need that. So this is fixed. But later on, when we run different particle size, then you should change this number. Okay? And the polarization is also something that you can change. And as of setting of now, in the DDSCAT, the light is always going in the X direction, which is Z direction. Okay, so the light polarization, of course, cannot be in the X direction, right? Electromagnetic wave, the electric field is always perpendicular to the light propagation field. Okay, so this is always 0, 0. And so when you set 1, 0, that means that the electric field is linearly polarized in the Y direction. If you somehow set this 0, 0 and set the third number is 1, 0, then that means the electric field is polarized in the Z direction. Okay, so you need to know that you have an option here. And we will also study circularly polarized light. And circularly polarized light is specified by changing the number here. All right. So right now, let's do just linearly polarized light. And the orthogonality is why sometimes we worry about it, we don't. And another thing that we worry about is rotation of the gold nanoparticle assembly. So these are controlled over here: beta min, beta max, and beta, theta min, theta max, and etc. But let's not worry about these for a moment. And the rest, you just leave it there. You don't really have to change too much. And actually the bottom is target frame or lab frame, not needed, well, leave it there. So that you finish preparing this DDSCAT.pol and DD postprocess.pol. This test run, I really didn't calculate the near field, so it's actually not going to use in the DD postprocess. I'm not going to worry about it, but you leave it there. You just copy this whole directory file outside into your own directory. Okay. Once you prepare this file, which contains all the input file, you need to prepare copy another thing called submit. It's a scripting file that we write called where is it? Okay, I'm gonna go to, it's in my it's in, okay, circular polarization submit very I don't want this one. It's one on a particle. Okay. Gold. I'm running something here. So I'm copying from my directory 80 nanometer Z array, submit very lambda array dot ship. Copy this one to here. And also there's another one called get output array dot ship. Okay? Get output. So you can copy these two files from my directory. So remember, I put this everything in the test student. So you literally just copy everything from test student. You should have a thing. And then let me explain. So this one is the one that you talk to the job queuing system on our HPC. So these that comes like that, okay? So you don't have to worry too much. This is the setting that we write up this scripting for the student to use. But you can kind of see the command is always sbatch, and then it's asked to use 8 CPU, 8 processor on one node, and the memory is like 32 gig, okay? And the job name, you can give some meaningful job, DDSCAT, this is double precision version, and maybe test, okay? And then others you don't touch these, all right? And so notice this, like, this is a scripting, it's a C shell. So set lambda equal 0 dot and slum array task ID. Yeah, so slum array task ID is specified here. It's a 400 to 900 by increment of 5. So that means it's gonna create this lambda gonna be about 0.4 and then 0.405. You know what I mean? It's like 400 to 900. So it's basically gonna create an array of the integer from 400 to 900 in increment of 5. So you set the lambda value equal that, and then it will do lambda equal whatever the value, and then it make a directory called lam, and then this slum array task ID. So you will see once I run this scripting, it will create a directory called lambda 400, lam 400, lam 405, lam 500, etc. And then what it does, it will change into that directory that you just created, and then it's gonna make a directory name. Okay, yeah, it is this change cd slum submit directory is where you start submitting on job, which right now it's here. So this is where I put submit very lambda array dot shell. So I'm gonna start here. This is the where you submit the job, and then it will make a directory called directory name, where the directory name is set over here. So that's how you make a directory lam 400, lam 405, and then you need to make sure you copy in the input file everything to this. Usually we should copy dash items. So by copying files, everything to that directory. Okay. All right. And then afterwards, yeah, copy file. All the files that input, it put in the directory name. And then it will change the DDSCAT.py file, the lambda value, to the real numerical lambda value. All right. And then these two lines specify the code that we will run. The DDSCAT executable is pointing to the executable file sitting in this directory, /home Jimball, DDSCAT1, SRC. So we compile this DDSCAT ourselves. So that's why the executable is sitting in one of my students' directory. So you should use this. You don't mess around with that. And DD post-process executable is also in that directory. And then set this and echo start. And then you just, to run the job, you say DDSCAT _ execute to DDSCAT log, and you finish, and it will do it. Okay. So this is, so make sure you copy this. And to run this job, so I'm going to submit very lambda. Did you see I've already put the notes here? To use this, you just say sbatch and then submit very lambda array.shell. Okay. And I'm not going to submit it. You should submit it and you should run it. And after you finish all the run, then you use this get output array.shell to get all the results. And I'm going to give you a little bit look. Get output array.shell will actually, after you finish all the run, it go to every directory and it extract out the data. Okay, what's the wavelength and what's the extinction coefficient, what's the absorption, scattering, E-square, average, and surface to the file called the combined value.tag. And then that's the data set that we will use. So I'm going to get, instead of running this, I'm going to go to another directory where I had ran some of the data. So for example, let me see, the circular polarized. Okay, so for example, I'm going to show you 1 nanoparticle, a reason that I'm running. Gold sphere, 10 nanometer, right? Did you see how like my directory contain all the lamp, and so that's how you get after you submit very lambda array.shell, and the computer will run all of these. And in each directory, if you go to lamp 400, and you can see that it copied the files in the subdirectory of the files, and then put everything here and finish running. And then after you ran this, after you finish run, now this one you can rerun it, like share get output array.shell. I'm going to rerun it. It's just fine. It's just going through all of the directory again and extracting the data out. And so this is just again. And then you have this file called combined value.txt. And this is the file that needs to be transferred into the Excel file. But I'm going to use GNU plot. You still remember GNU plot? To plot this. Now, to use the GNU plot, you should probably turn on, install something called Xming, Xming, and run the Xming. Then you can plot this combined value.txt, and then you can say using column 1, 2, okay? And then you get a plot. So this is the, there we go, okay? So this is the extinction spectrum of gold nanoparticle. Here's lines and points. Yeah, gold nanoparticle, and the x-axis is actually wavelengths from 400 nanometer to 900 nanometer already. Okay, this is the extinction coefficient, how it varies with lambda. And you can also plot 1-3. Okay, this is the called absorption. So but there is a little bit scattering for this particle, but very little. So if I plot just combined value 1-4, this is the lambda versus the scattering. So the scattering signal is very low. But we also calculated in this particular run, I have also calculated near field. So you can plot the near field spectrum and how it look like. The near, and you know, I know you don't know what's the meaning of all of referring to, but you can catch up later. Near field is 1-5, so that's how. But in the round that if you don't perform near field, then you wouldn't have the column 5, column 6. Okay, so good luck. I would ask you to first, yeah, make sure go to my DDSCAT, go to my test students, okay, and then copy these things. Go to 50 nanometer is an example. I'm also gonna copy this submit array shell in the front and copy get output array share. So I have many copies. So you can just copy these from me. And then you can try test run. So I would give you a chart. See if you can successfully run 50 nanometer spectrum and see what is the gold absorption spectrum 50 nanometer gold look like. Okay, a solution of gold nanoparticle. All right, so that is our quick introduction how to run DDSCAT job. Oh, by the way, I can also show you a few things. The Slurm, the job queuing system. And if you wanted to see what's going on, you do SQUEU, right? SQUEU, yes, SQ. So you can see it, there's a lot of jobs. Now, I can tell you, I have aliased my command SQ. I created an alias called SQ is SQ-L-UY1. So that way, when I type SQ, I don't look up other people's job. I can just look up what my job has. So currently, if I type SQ, you can see this is me, and I have 1, 2, 3 jobs queued, and one of them is running. Okay, so you may want to also add this. What is it over here? The alias here. Alias SQ, where's the alias SQ here? Alias SQ, and copy exactly this SQ-L-U, and replace Y1 by your username. Then you can look up if you have any job running very quickly. Okay, I think that should be a good introduction for you. So enjoy and try having fun. Let me see. Where is it? Where's the meeting?